Welcome to Bedtime Express, your destination for slow, dreamy storytelling that guides you gently into restful sleep. I'm your narrator, and tonight we embark on a 3-hour journey into the hidden world of scientific discovery. Before you fall asleep, please like this video, leave a comment sharing your thoughts, and subscribe to Bedtime Express for more fascinating bedtime stories. Your support helps us continue creating peaceful, immersive content designed to help you relax and sleep deeply. You're about to explore Benjamin Franklin's secret experiments, the lesser-known scientific pursuits and private investigations of America's most versatile founding father. Beyond the lightning rod and the bifocals, Franklin conducted countless mysterious experiments in his quiet laboratory, exploring electricity, water, heat, light, and the fundamental principles of nature itself. Discover the stories of his patient observations, his careful measurements, and his relentless curiosity that drove him to understand the world around him. So find yourself a comfortable place, dim the lights, and prepare to drift away as we explore the wonders of Franklin's scientific mind. Allow our slow, soothing narration to ease you towards sleep. Now take a deep breath, close your eyes, and let the story begin. Benjamin Franklin's Secret Experiments. Close your eyes and imagine yourself transported back to the 1800s, to a time when the world was quieter, slower, and filled with mystery. Picture a modest printing shop in Philadelphia, its windows glowing softly with candlelight as the evening deepens into night. Inside, amid the gentle clatter of metal type and the smell of ink and parchment, there exists a man whose mind never quite stops exploring, never quite stops wondering about the fundamental nature of the world around him. This man is Benjamin Franklin, though he is not yet the famous figure you might imagine him to be. When we think of Benjamin Franklin, our minds often turn to his most celebrated achievements: the lightning rod, the bifocals, his diplomatic triumphs, his contributions to American independence. These are the monuments of his public life, the achievements etched into history books and remembered in classrooms across the world. But what we often overlook, what remains nestled in the quieter corners of history, are the experiments that occupied his restless mind during the long evenings when the printing work was done and the city outside had fallen into sleep. These are the secret pursuits, the private investigations into nature's mysteries that drove this extraordinary man forward, night after night, year after year. Before Franklin became the statesman, before he became the lightning collector and the inventor of devices that would change the world, he was something perhaps more essential. He was a curious mind in a world that was just beginning to ask the right questions about how things worked. In the early days of his life in Philadelphia, when he was still establishing himself as a printer, Franklin would spend his evenings not with society, not with the important men of the city, but alone or with a handful of trusted friends, conducting experiments that seemed strange and pointless to most observers. Yet these experiments, these private investigations, would eventually illuminate pathways that the scientific world was only beginning to explore. One of Franklin's earliest and most fascinating secret pursuits involved the study of electricity, though electricity in those days was scarcely understood at all. Picture Franklin in his workshop, perhaps holding a glass rod in his hand, carefully rubbing it with fur or silk until it becomes charged with what people then called the electrical fire. He would watch, mesmerized, as small particles of paper or feathers would dance and jump toward the rod, attracted by some invisible force that seemed to defy all rational explanation. To the common observer, this might have seemed like magic, witchcraft even, but Franklin saw something different. He saw the underlying order of nature expressing itself in these small, delicate movements. Night after night, Franklin would repeat these experiments, varying the materials he used, the intensity of his rubbing, the conditions of the room. He kept meticulous notes, observations recorded by candlelight in handwriting that grew more hurried as fatigue set in but never ceased to be precise. What was this invisible force? Where did it come from? Could it be harnessed, controlled, understood? These questions became an obsession, a gentle obsession that would occupy much of his spare time for many years to come. During these early investigations, Franklin began to develop a theory that was revolutionary for its time. He proposed that electricity was not, as some believed, a special fluid or fire that was completely separate from the material world, but rather a natural force inherent in all matter. This was a radical thought, one that required him to reconsider the entire framework through which people understood the physical world. He began to speak of electricity in terms of positive and negative charges, concepts that might seem commonplace to us now, but were genuinely innovative for the 18th century. But Franklin's curiosity extended far beyond the laboratory. Even as he was conducting these electrical experiments, his mind was simultaneously engaged with other mysteries. He became fascinated by the behavior of water, by the way it moved through pipes and channels, by the patterns it made when it flowed and when it was still. He constructed small models in his workshop, channels and dams of wood and stone, through which he would direct water to observe how it would move, how it would pool, how it would respond to different configurations of its path. This was experimentation at its most fundamental, simple observation, careful note-taking, and the gradual accumulation of understanding. One particular experiment involving water captured Franklin's imagination for several years. He became convinced that by understanding the principles that governed water's movement, he might be able to design better systems for managing water in cities. He imagined in the quiet privacy of his workshop great reservoirs and aqueducts, that could supply cities with fresh water, keeping the inhabitants healthy and preventing the diseases that arose from standing water and poor sanitation. This was prescient thinking, ahead of its time, for Franklin was envisioning improvements to urban infrastructure that would not become commonplace for another 100 years or more. As the years passed and Franklin's reputation grew, he would continue these private experiments, often working alone late into the night. There was something deeply satisfying about this work, something that fed a part of his soul, that his public life, important as it was, could never quite satisfy. The printing business required him to be practical, efficient, concerned with the bottom line of profit and loss. But these experiments in his workshop allowed him to indulge another side of his nature, the dreamer, the philosopher, the person who looked at the world and asked not just how it was, but why it was that way. During this period, Franklin also began to observe and experiment with the study of meteorology, the study of weather and the atmosphere. He would track the movement of storms across the region, noting the wind directions, the changes in barometric pressure, the formations of clouds. He kept detailed records of temperature readings, sometimes taking measurements multiple times per day, gradually building up a picture of how the weather in Philadelphia changed throughout the year. This data, which might seem trivial to us now, was genuinely valuable in an age when meteorological understanding was almost non-existent. One night, as Franklin stood on the roof of his house watching a storm approach from the west, he experienced a moment of profound insight. The lightning that flashed across the sky, the thunder that rolled and echoed, these were not arbitrary natural phenomena, he suddenly understood, but expressions of the same electrical force that he had been studying so carefully in his laboratory. The realization struck him with almost physical force. Lightning was not fire from heaven, not divine punishment or natural disaster in the way that people understood it, but rather the discharge of electrical energy accumulating in the atmosphere. If this was true, then surely, he reasoned, there must be a way to protect buildings from lightning strikes by providing a controlled pathway for this electrical discharge to reach the earth safely. This insight, born from years of patient observation and careful experimentation, would eventually lead to one of Franklin's most important practical inventions, the lightning rod. But in the quiet of that night, as the storm drew nearer and the wind began to whip through the streets of Philadelphia, Franklin did not yet know that his abstract investigations would bear such practical fruit. He only knew that he had glimpsed something true about the nature of the world, and that he needed to continue his investigations to understand what this truth meant. As he climbed down from the roof and returned to his study, Franklin found himself thinking about the nature of discovery itself. Most of the great accomplishments of human civilization, he reflected, came not from the efforts of those who set out deliberately to achieve great things, but from the patient, persistent investigation of those who simply wanted to understand. The great inventors and discoverers were not necessarily ambitious in the conventional sense. Rather, they were driven by an almost childlike curiosity, a need to know, a desire to peer beneath the surface of things and glimpse the machinery of creation at work. He resolved, in that moment, to protect and nurture this quality in himself, no matter what other obligations and duties might arise in his life. Now imagine it is the 1750 seconds, and Franklin, though still not yet 60 years old, is becoming known throughout Philadelphia and beyond as a man of science and learning. His printing business has prospered, and he has gradually begun to free himself from the daily demands of commerce, allowing more time for his experiments and investigation. The hypothesis that he had formed that lightning was electrical in nature has been consuming his thoughts more and more completely, and he has begun to think about how one might actually test such an outlandish idea. If lightning were electricity, he reasoned, then it should be possible to collect a sample of lightning and examine it to see if it possessed the properties of the electrical force he had been studying so carefully. The challenge, of course, was how to collect lightning safely. One could not simply hold up a metal rod in a lightning storm and expect to survive the experience. Indeed, Franklin was well aware that this would almost certainly be fatal. But as he thought about the problem, an idea began to form in his mind, an idea so elegant and so daring that it could only have come from a mind that had already spent years studying electricity and understanding its properties. What if one were to use a kite, that common children's toy, to lift a conductor high into the storm clouds where the electrical charge accumulated? What if, at the end of this kite string, one attached a device that could draw off a small portion of the electrical energy without subjecting the experimenter to a lethal shock? Is less than #2. 0 is greater than. The famous kite experiment, that moment when Franklin flew a kite in a thunderstorm and proved that lightning was electrical in nature, is well known to history, taught in schools, depicted in paintings and illustrations. But what is less often discussed are the months of careful preparation that preceded this famous experiment, the dozens of smaller trials and tests that Franklin conducted to develop the technique safely and validate his hypothesis before he would dare to attempt the final dramatic proof. This is the secret history of the kite experiment, the hidden part that reveals Franklin not as a dramatic genius of sudden inspiration, but as a patient scientist who left nothing to chance. In the weeks before the famous kite experiment, Franklin conducted numerous trials with smaller electrical sources. He would erect poles in his yard and run wires from them down to conductors placed on the ground, observing how the electrical charge would flow through different materials and configurations. He tested various materials for the kite and the string, examining how each would respond to electrical charge without burning up or breaking. He designed and redesigned the method by which he would collect the charge, considering different types of devices that might safely draw electrical energy away from the kite string so that it could be stored and examined. One particularly clever device that Franklin developed during this preparatory period was an ingenious arrangement of bells and clappers that would be activated by electrical charge flowing through them. The bells would ring whenever electrical charge was present, providing both an audible warning to the experimenter that he was dealing with a live charge and a visible demonstration that the charge was actually present in the system. This simple innovation, born from practical necessity, became one of his beloved experimental tools, and he would use it in dozens of different contexts as his investigations continued. When Franklin finally prepared for the actual kite experiment in June of 1752, he did so with extraordinary caution. He selected a location that was open and elevated, where lightning would be likely to strike, but where he could also protect himself adequately if something went wrong. He chose a stormy day, but not the most violent storm, not the most extreme weather conditions, but rather a day of moderate storms that presented significant electrical activity while remaining somewhat manageable. He did not perform this experiment alone, despite the historical depictions that often show him as a solitary figure, but rather brought his son William with him, so that if anything went wrong, there would be another person present to provide assistance or help in case of emergency. The experiment itself was almost deceptively simple in its execution, yet it required absolute precision and careful attention to detail. Franklin held the kite string in his hand, but importantly, he protected his hand with a silk ribbon, which does not conduct electricity and thus would insulate him from direct contact with the charged string. The kite itself was constructed from common materials, wood frame, and paper such as any child might use to make a kite for play. At the end of the kite string, Franklin had attached a metal key, a common household object, and from this key, a wire ran down to another metal conductor placed on the ground. This system allowed electrical charge to flow from the clouds, through the kite, down the string, into the key, and eventually into the ground, all the while allowing Franklin to observe and, if desired, to collect a sample of the charge for examination. As the storm gathered above them, Franklin held the kite steady, keeping it positioned high in the air where the electrical activity would be most intense. For a time, nothing happened. The sky churned with clouds, and distant lightning illuminated the landscape, but no charge came down the string to Franklin's hand. Minutes passed, which must have felt like hours to Franklin and his son, waiting in the storm, exposed to the elements, uncertain whether the experiment would produce any results at all. Then, gradually, Franklin noticed something extraordinary. The loose fibers of the hemp string began to stand up, pointing away from the string itself, as if they were being repelled by some invisible force. This was the effect of electrical charge accumulating in the string, and Franklin's heart must have quickened at the sight. He moved his finger carefully toward the metal key at the end of the string, not quite touching it but coming close enough to see a spark of electricity jump between his finger and the key. The spark was small, almost delicate, nothing like the violent discharge of a full lightning bolt, but it was unmistakably electrical in nature. Franklin had done it. He had captured lightning from the sky and held it in his hand, and in doing so, he had proven definitively that lightning was not some supernatural phenomenon or divine expression of God's will, but rather a natural force governed by the same principles that he had been studying for so many years in his laboratory. The implications of this discovery were profound and far-reaching. If lightning were merely electricity, then the great and terrible power that had terrorized humanity since the beginning of time could potentially be predicted, controlled, and even neutralized. Franklin began to develop his ideas for the lightning rod, a practical application of his theoretical discovery that could protect buildings and lives from the destructive force of lightning strikes. The lightning rod was simple in concept, a metal conductor running from the top of a building down to the ground, providing a safe pathway for electrical discharge from a lightning strike to flow into the earth without passing through the structure of the building itself or the people inside it. But Franklin's secret investigations did not stop with the practical application of lightning protection. In his workshop, he continued to explore the nature of electricity itself, conducting numerous experiments designed to answer the fundamental questions about what electricity was, how it worked, and what its properties might be. He designed experiments to determine whether electricity could be stored, and if so, for how long and in what quantities. He built what are now called capacitors, devices that store electrical charge, though of course he did not use that term. One of his most famous capacitor designs involved two metal plates separated by glass, which he called his electrical battery, a name that would eventually be adopted for all devices that store and release electrical energy. During this period of intense investigation, Franklin also discovered what is now known as the effect of electrical conductivity, the fact that some materials allow electricity to flow through them readily, while others resist the flow and may accumulate charge instead. He classified materials into what he called conductors and non-conductors, designations that are still used today in electrical science. He observed that metals were universally good conductors, while materials like rubber, glass, and amber were poor conductors or insulators. This systematic investigation of material properties was crucial for the development of electrical engineering, allowing future scientists and engineers to understand which materials to use in different applications. One of Franklin's most curious experiments during this period involved what he called electrical healing. He became convinced that electrical charge might have therapeutic properties, and he conducted numerous tests on his own body and, with permission, on the bodies of friends and acquaintances, is less than #0. 5 is greater than. He would apply electrical shocks to different parts of the body and carefully observe and record any sensations or effects that resulted. Though the therapeutic claims he made were largely unfounded, electricity has very limited genuine medical applications. This line of investigation was not entirely without merit, as it led to a better understanding of how electrical current affects living tissue, knowledge that would eventually prove valuable in fields like neurology and cardiology. Another of Franklin's private scientific pursuits during this period involved the study of heat and temperature. He became fascinated by the question of how heat moved through different materials and by different mechanisms. He designed experiments in which he would carefully observe how heat radiated from one object to another, how it traveled through conducting materials, and how it accumulated in different substances. He noted that different materials absorbed and retained heat differently, and that the color of a material seemed to influence how much heat it would absorb from the sunday. These observations, made in the quiet of his laboratory, represented early investigations into what would later become the field of thermodynamics, one of the fundamental branches of physics. During one particularly contemplative evening, Franklin sat alone in his study, surrounded by instruments and apparatus from his electrical experiments, and began to reflect on the interconnectedness of all natural phenomena. He had been studying electricity, heat, water, and light as if they were separate forces, each operating according to its own principles. But what if they were not separate at all? What if they were all manifestations of a single, underlying principle of nature? This was the beginning of his thinking that would eventually contribute to the development of the law of conservation of energy, one of the most fundamental principles in all of physics. Though Franklin did not himself formulate the law in the way that later scientists would, he was among the earliest thinkers to recognize that energy in various forms could be transformed from one state to another without being created or destroyed. As the decade of the 1750 seconds drew to a close, Franklin's electrical investigations had earned him international recognition. Learned societies across Europe were discussing his work, and scientists in Paris and London were conducting their own experiments based on his methods. Yet, despite this external recognition, Franklin continued to conduct his experiments with the same patient, methodical approach that had characterized his work from the beginning. He knew that the greatest discoveries often came not from pursuing fame or recognition, but from the simple, persistent desire to understand the world more fully. As we move forward in time to the 1760 seconds and 1770 seconds, we find Franklin engaged in yet another fascinating set of private investigations. By now, his life had become increasingly complex. He had become a postmaster, a politician, a diplomat, and a representative of the Pennsylvania Assembly. His time was more fragmented than ever, divided between public duties and private pursuits. Yet somehow, in the remaining hours of his days, in the evenings and early mornings, when the rest of Philadelphia slept, Franklin maintained his laboratory and continued his experiments with undiminished passion and curiosity. During this period, Franklin became deeply interested in the problem of human vision and the correction of refractive errors in the eye. He had long worn spectacles, as do many people as they age, and the lens of the eye begins to lose its flexibility and ability to focus on objects both near and far. But Franklin, being Franklin, did not simply accept the inconvenience of this condition. Instead, he set about trying to solve it. He began his investigations by studying the anatomy of the eye in great detail, reading anatomical texts, and conducting his own observations whenever the opportunity arose. The problem, as Franklin understood it, was that a person who needed to focus on objects at different distances would require two different prescriptions for their lenses, one for near vision and one for distance vision. Most people in that era simply accepted this limitation, switching between different pairs of spectacles as needed, or choosing to focus on one distance or another for much of the day. But Franklin, with his characteristic ingenuity, began to imagine a different solution. What if one could combine two lenses into a single pair of spectacles, with one portion of the lens ground for near vision and another portion for distance vision? Over a period of several years, working in collaboration with lens makers and optical craftsmen, Franklin developed what he called his bifocals, spectacles with lenses divided into two sections, the lower portion for close work and reading, the upper portion for distance vision. The innovation seems almost obvious to us now, but in the 18th century, it required careful experimentation and precise calculation to determine the correct arrangement of the two focal lengths and the exact position at which the division between the two sections should occur. Franklin conducted numerous trials, testing different configurations and gathering feedback from friends and colleagues who tried on the prototypes. What is less well known is that Franklin continued to experiment with his bifocal design long after he had produced a working prototype. He tried different materials for the lenses, different shapes for the frames, different positions for the dividing line between the sections. He investigated whether the transition between the two portions of the lens could be made smoother or more gradual. He conducted experiments to determine the optimal size of each lens section for different types of tasks and different positions of the eye. This ongoing refinement This secret continuation of development work after the original invention was complete exemplifies Franklin's approach to invention not as a single moment of inspiration, but as a process of continuous improvement and optimization. Another of Franklin's laboratory investigations during this period involved the study of water and its properties. He had always been fascinated by water, and as he aged, this fascination grew deeper and more sophisticated. He designed experiments to study how water evaporates and how this process is affected by temperature, humidity, and other atmospheric conditions. He conducted careful measurements of the density of water at different temperatures, noting that water behaves in an unusual way, becoming less dense as it cools near freezing, which is why ice floats. He explored the properties of different types of water: salt water from the sea, brackish water from estuaries, fresh water from springs and streams, trying to understand how the presence of dissolved substances affected the water's behavior and properties. During his investigations of water, Franklin became particularly interested in the phenomenon of surface tension, though of course the concept did not yet have a name. He observed that water formed droplets rather than spreading out as a thin film across a surface, that insects could walk on the surface of water without sinking, and that water could climb up the sides of narrow tubes against what seemed to be the force of gravity. He designed elegant experiments to explore these properties, carefully observing the behavior of water in different circumstances and recording his observations in meticulous detail. Though he did not fully understand the mechanism behind surface tension, for this would require knowledge of molecular forces that would not be developed for many decades, his observations were accurate and insightful. Franklin also became interested in the study of what we would now call hydrodynamics, the behavior of moving water and how water flows through different configurations of channels and openings. He designed scale models of rivers and estuaries, constructing them in his laboratory with careful attention to recreating the conditions of the real systems he was studying. He would release water into these models and observe how it would flow, where it would pool, how it would respond to different obstacles and configurations. In his notes, he speculated about how this knowledge might be applied to improving navigation of rivers, managing water resources for cities and farms, and preventing erosion and flooding. One particular area of Franklin's investigation that remained quite private, discussed only in his correspondence with a few trusted scientific colleagues, involved his observations of human physiology and medicine. Franklin was not a physician, nor did he claim to be, but he was deeply interested in understanding how the human body worked and what might be done to maintain health and treat disease. He conducted observations of the effects of different environmental conditions on human health, noting how temperature and humidity affected energy levels and susceptibility to illness. He studied the effects of different types of foods and beverages on digestion and overall well-being. He even conducted early experiments investigating the effects of exercise and rest on human vitality. In his private correspondence, Franklin discussed his belief that many of the illnesses that affected people of his time were related to environmental factors that might be controlled or improved. He advocated for better ventilation in buildings, for clean water supplies, for the removal of standing water that was known to breed disease. He recommended regular exercise and fresh air as means of maintaining health. These ideas, which seem commonplace to us now, were genuinely innovative in the 18th century, when medical science was only just beginning to connect environmental conditions to health and disease. Franklin also invested considerable effort during this period in studying what we would now call acoustics, the science of sound and how it travels through different media and spaces. He conducted experiments with various instruments, observing how sound traveled through air, through water, and through solid materials. He experimented with different configurations of rooms and spaces to understand how their shape and materials affected how sound would reflect and propagate through them. He was particularly interested in understanding why some spaces seemed to carry sound very well, allowing a whisper to be heard across great distances, while other spaces seemed to muffle and absorb sound completely. During this period, Franklin maintained detailed journals of his experiments and observations, though he was careful to be selective about which of these observations he shared publicly and which he kept private for his own reference. The distinction between public and private scientific work was important to Franklin for several reasons. Some of his experiments were inconclusive or led to dead ends, and he felt no obligation to share incomplete or speculative work with the public at large. Other investigations were of a more personal nature, explorations of ideas that interested him but that might not be of general interest or importance. And in some cases, particularly as he became more involved in matters of political and diplomatic importance, Franklin was cautious about what he published, concerned that certain lines of investigation might attract unwanted attention or controversy. One of Franklin's most intriguing private pursuits during this period was his investigation into the nature and properties of air. He became convinced that air was not, as many believed, a simple uniform substance, but rather a complex medium composed of various components with different properties. He conducted experiments in which he would carefully collect air samples from different locations and at different times of day and season, then analyze their properties. He observed that the composition of air seemed to vary subtly depending on location and weather conditions, and he speculated about the significance of these variations. Franklin was particularly fascinated by what we would now call atmospheric electricity, the presence of electrical charge in the atmosphere itself, distinct from the charge present in lightning storms. He conducted numerous experiments designed to detect and measure this background electrical charge, developing sensitive instruments that could pick up traces of electrical activity even in clear weather, when lightning was not present. His observations suggested that the atmosphere was always charged with electrical energy to some degree, an insight that would not be fully explored and explained until more than a century later, when scientists developed a more complete understanding of atmospheric electricity. In one of his more poetic reflections, Franklin noted in his private journals that the natural world seemed to be constantly in motion, constantly exchanging energy and matter in an intricate dance that connected all living and non-living things. He observed that heat seemed to flow from warm objects to cold ones, that water evaporated and then fell again as rain, that electrical charge seemed to accumulate and discharge in endless cycles. He wondered whether all of these phenomena might be manifestations of some deeper principle, some fundamental law of nature that governed the exchange and transformation of energy throughout the world. This intuition, born from decades of careful observation and experimentation, represented early thinking about energy conservation and the laws of thermodynamics that would not be formally developed for many decades to come. As Franklin moved into his 70s and then his 80s, his experimental work continued, though necessarily at a slower pace than in his earlier years. He maintained his laboratory space and his instruments, and he continued to conduct investigations on topics that fascinated him. He never completely retired from his scientific pursuits, never completely closed the door on investigation and discovery. For Franklin, science was not simply a profession or a sideline activity. It was a fundamental aspect of who he was, a way of engaging with the world that had never grown old or lost its appeal, no matter how much else in his life had changed and evolved. Now let us turn our attention to another dimension of Franklin's secret investigations, his work on practical improvements to everyday life, the kinds of investigations that occupied much of his time during the years when he had become not only a scientist, but also a man of political power and influence. During his years in Pennsylvania and later in other colonies and nations, Franklin conducted numerous experiments and developed numerous inventions designed to address practical problems and improve the quality of life for ordinary people. One of Franklin's earliest private pursuits in this direction involved the design and testing of improved heating and cooling systems for buildings. During the long winters of Philadelphia, the city would become bitterly cold, and the only means of heating most buildings was through open fireplaces, which were tremendously inefficient. Much of the heat would escape up the chimney rather than warming the room. Franklin became convinced that he could design a better heating system, one that would capture more of the heat and distribute it more effectively throughout the building. Over a period of several years, Franklin worked on what he called the Pennsylvania fireplace, a design that would become widely known and used, though it is often remembered by its later name, the Franklin stove. The basic principle of his design was elegant in its simplicity. The stove would be constructed as a hollow box with interior baffles that would direct the hot gases and embers through a more complex path before they reached the chimney, allowing more of the heat to be transferred to the surrounding air before escaping outside. Additionally, the stove would be positioned so that it could heat a larger space than a fireplace could, and it would consume less fuel to produce the same amount of heat. But what is less well known is that Franklin continued to refine and improve his stove design long after the initial model had been developed and adopted by people throughout the colonies. In his workshop and through correspondence with other craftsmen and engineers, he experimented with different materials for the stove, different shapes and configurations for the interior baffles, different methods of construction that would make the stove stronger and more durable. He conducted measurements of the efficiency of different designs, carefully comparing the amount of fuel consumed to the amount of heat produced, always looking for ways to improve the performance. Another area of Franklin's practical investigations involved water supply and sanitation in cities. Franklin had long been concerned about the quality of drinking water in Philadelphia and other urban areas, and he conducted investigations into the best means of providing safe, clean water to the population. He designed systems of conduits and pumps that could deliver water more efficiently and with less contamination. He experimented with methods of filtering and clarifying water to remove sediment and improve its quality for drinking and cooking. He investigated the effects of different pipe materials on the quality of water traveling through them, noting that some materials would react chemically with the water in ways that could affect its safety and taste. During one particularly productive period in the 1,760 seconds, Franklin conducted a series of experiments investigating whether water could be purified by exposure to sunlight, a line of inquiry that anticipated modern understanding of UV disinfection by more than a century. He placed samples of water in clear glass vessels and exposed them to direct sunlight over periods of days and weeks, then examined them for changes in clarity, odor, and the presence of small organisms visible under magnification. Though he did not fully understand the mechanisms involved, he noted that water treated in this way seemed to remain fresher longer than untreated water, suggesting that sunlight had some beneficial effect on water quality. Franklin also became intensely interested in the problem of preventing disease in crowded urban environments. He observed that diseases seemed to spread more rapidly in areas with poor sanitation, where standing water accumulated and where sewage was not properly managed. He conducted investigations into how diseases might be transmitted, developing theories about bad air and miasmas that, while not entirely correct in their mechanisms, did lead to practical recommendations for improving sanitation and ventilation that actually did help prevent disease spread. He advocated for the systematic removal of waste from cities, the cleaning of streets, and the improvement of drainage systems, recommendations that seemed obvious to later generations, but were actually quite innovative for his time. Another fascinating area of Franklin's practical work involved his investigations into the properties of light and color. He conducted numerous experiments with different types of colored glass and cloth, observing how different colors absorbed or reflected light, and how this affected the temperature of objects exposed to colored light versus white light. He noted that dark colors seemed to absorb more heat from sunlight, while light colors reflected more of the light and heat away. This observation led him to practical recommendations about the colors of clothing for different seasons and the colors used to paint buildings in different climates to help manage temperature. In one particularly elegant series of experiments, Franklin investigated the melting behavior of snow and ice, particularly the effects of different colored materials placed on top of snow. He would place pieces of different colored cloth on clean snow and observe how quickly the snow would melt beneath each color, comparing the results carefully. He found, as expected, that dark colors absorbed heat more readily and caused faster melting, while light colors reflected the heat and caused slower melting. This simple investigation held practical implications for understanding how to manage snow accumulation and how the natural colors of the landscape affected seasonal temperature changes. Franklin also devoted considerable effort to the study and improvement of what we would now call transportation systems. He conducted experiments on the physics of motion, studying how friction affected the movement of objects across different surfaces. He investigated the design of wheels and axles, seeking to understand how they could be constructed more efficiently to reduce friction and allow heavier loads to be moved with less effort. These investigations were driven by his concern for the practical challenges of moving goods and people across distances, challenges that were significant in the 18th century, when all transportation relied on human or animal power. As Postmaster of Philadelphia and, eventually, as Postmaster General of the colonies, Franklin became interested in the practical problems of mail delivery and communication over distance. He conducted investigations into the fastest and most efficient routes for mail carriers, studying maps and actually traveling routes himself to time how long they would take. He designed improved mail containers and organizational systems that would allow mail to be sorted and delivered more efficiently. He even conducted experiments with different materials for writing surfaces and inks, seeking to find combinations that would be more durable and less likely to fade or deteriorate during the long journeys that mail undertook. One of Franklin's more whimsical but nonetheless serious investigations during this period involved the design and testing of improved swimming techniques. Franklin was an enthusiastic swimmer and strong believer in the health benefits of water exercise. He conducted experiments investigating how different body positions and movements would allow for more efficient swimming, and he designed special paddle-like devices to be worn on the hands and feet to increase the propulsive force of swimming movements. He documented his findings in detailed notes and even designed diagrams showing the proper body position for efficient swimming investigations that anticipated by more than a century the systematic study of aquatic locomotion. Franklin also became interested in the problems of marine transportation and ocean travel. He conducted numerous investigations into the currents and winds of the Atlantic Ocean, gathering information from ship captains and sailors regarding ocean conditions at different seasons and in different locations. He began to map these currents and wind patterns, creating some of the earliest systematic representations of what we would now call the North Atlantic circulation patterns. One particular current that fascinated him was the warm water current that flowed north along the American coast before crossing toward Europe, a current that we now call the Gulf Stream, though Franklin did not give it that name. Franklin's investigations into ocean currents were driven by a practical concern. Mail ships traveling from America to Europe could take very different lengths of time, depending on what season they traveled and what route they took. By understanding the patterns of currents and winds, he reasoned, it might be possible to route ships more efficiently, reducing travel time and therefore getting mail to its destination more quickly. He corresponded with ship captains and carefully documented their observations of ocean conditions, gradually building up a more complete picture of the ocean's behavior. This work anticipated the development of oceanography as a scientific discipline by many decades. Another area of Franklin's investigation that reflected his concern for practical improvement involved the design of better lighting systems. The candles that were universally used for lighting in the 18th century were inefficient and often smelly, produced from animal tallow and emitting smoke and unpleasant odors as they burned. Franklin conducted experiments investigating whether improved candles could be made from better materials, and he studied the principles of flame and combustion to understand what affected the brightness and efficiency of light produced by a burning flame. While he did not revolutionize candle-making technology, his investigations contributed to understanding the principles that would eventually be applied to improved lighting systems. During this period, Franklin also maintained a strong interest in the study of clocks and timekeeping, a practical concern of significant importance in an era before electronic timekeeping was possible. Accurate timekeeping was essential for navigation at sea and for the coordination of activities in urban centers. Franklin studied the design of pendulum clocks and conducted experiments investigating different materials and configurations for clock mechanisms. He was particularly interested in understanding how temperature changes might affect the accuracy of clocks. since clocks were subject to expansion and contraction as temperature varied. Another fascinating area of Franklin's practical investigations involved his work with acoustics and hearing. He conducted experiments attempting to design a hearing aid for the deaf and hard of hearing, investigating how sound vibrations could be transmitted through bone conduction and how sound could be amplified and directed more effectively to the ear. While his hearing aids, by modern standards, were crude and not very effective, the principles on which they were based, bone conduction and strategic amplification of sound, anticipated techniques that would be much more successfully developed in later centuries. Franklin also invested considerable time in investigating the properties of air currents and ventilation systems. He was particularly concerned with the problem of indoor air quality in crowded spaces like assemblies, theaters, and buildings where many people gathered for meetings or entertainment. He conducted experiments investigating how air moved through different configurations of windows and doors, how ventilation could be improved to remove stale air and bring in fresh air, and how air temperature affected the comfort and health of people in enclosed spaces. These investigations led to practical recommendations for improving ventilation in buildings, recommendations that were sometimes adopted in public buildings and theaters in the colonies. Throughout all of these varied practical investigations, Franklin maintained a consistent philosophy that science should not be purely abstract and theoretical, but should always have, as one of its goals, the improvement of human life and the solution of practical problems that affected ordinary people. He believed that the best science was science that was driven by real-world concerns, that emerged from careful observation of problems in everyday life and from a determination to find solutions that could be implemented and would make a tangible difference in people's lives. This philosophy guided all of his work, both the more theoretical investigations of natural forces and principles and the practical designs and innovations that bore his name. As we arrive at this final chapter of our exploration of Benjamin Franklin's secret experiments, let us pause and reflect on the broader significance of his life's work, both the investigations that were widely known and celebrated, and the private pursuits that occupied so much of his time and attention over the long decades of his life. Franklin lived during a time of tremendous intellectual ferment in Europe and America, a period when the scientific revolution that had begun centuries earlier was truly reaching its maturity, when the systematic investigation of nature was beginning to transform human understanding of the world. During Franklin's lifetime, the very concept of science itself was still being defined and refined. There was no formal scientific establishment as we know it today, no standardized scientific education, no regular scientific conferences and journals, no clear lines between what was considered legitimate scientific investigation and what was considered merely amateur tinkering or hobby work, Franklin thrived in this environment of flux and possibility, embracing a style of investigation that combined rigorous methodology with wide-ranging curiosity, precise measurement with creative insight, practical problem-solving with abstract theorizing. What strikes the modern observer when studying Franklin's life is the remarkable breadth of his interests and investigations. In the modern world, science has become highly specialized and compartmentalized. Physicists study physics, biologists study biology, chemists study chemistry, and rarely do these disciplines intersect or inform one another in any meaningful way. But Franklin, operating in a different era with different assumptions about what could be studied and how, pursued investigations across a remarkably wide range of disciplines. He was simultaneously a physicist studying electricity and optics, a meteorologist studying weather and atmospheric conditions, a physiologist investigating the properties of the human body, an engineer designing practical devices and systems, a naturalist observing the living world, and a chemist investigating the properties of materials. This breadth of investigation was not accidental or haphazard. It reflected Franklin's fundamental conviction that nature was unified, that the same underlying principles that governed the behavior of electricity also governed the behavior of heat, light, and motion, and that a complete understanding of nature required the investigation of all these phenomena and the search for the connections between them. In this respect, Franklin was far ahead of his time, anticipating the modern view of science as an interconnected web of knowledge rather than as separate disciplines. One of the most important legacies of Franklin's investigations was his methodology, his approach to discovering truth about the natural world through careful observation, systematic measurement, controlled experimentation, and the gradual accumulation of evidence and understanding. In an era when much scientific work still relied on pure reason and logical deduction from first principles, Franklin championed an empirical approach that insisted on checking ideas against reality through careful observation and measurement. This empirical approach would eventually become the foundation of modern science, but in Franklin's day, it was still relatively novel and was not universally accepted, even among those who considered themselves serious investigators of nature. Franklin's approach to experimentation also reflected an important principle that would eventually become central to scientific methodology, the principle of reproducibility. Franklin did not simply conduct an experiment once and announce his results. Instead, he repeated experiments multiple times, varying conditions, systematically to understand how different factors affected the outcome. He documented his procedures in sufficient detail that others could reproduce his experiments and verify his results. This commitment to reproducibility and verification was revolutionary in an era when much of what passed for science was based on testimony of authority rather than on the ability of anyone who wished to do so to independently verify the findings through their own investigations. Another significant aspect of Franklin's legacy involved his conviction that scientific knowledge should be shared and disseminated widely rather than being hoarded as a private possession or used for personal gain or aggrandizement. When Franklin developed the lightning rod, he deliberately chose not to patent it or seek to profit from it directly, but rather published his findings so that anyone who wished to do so could build lightning rods to protect their buildings. Similarly, though he invented the bifocals and the Pennsylvania stove, he did not attempt to monopolize the manufacture and sale of these items, but rather allowed knowledge of their design to spread widely so that many people could benefit. This approach to sharing knowledge reflected Franklin's belief in the common good, his conviction that scientific knowledge ultimately belonged to all humanity and should be used to benefit the greatest number of people rather than to enrich a few individuals. In this respect, Franklin was expressing values that would eventually become fundamental to modern science: the principle that scientific knowledge should be openly published and subjected to the scrutiny and criticism of the entire scientific community, the principle that science is ultimately a collective human enterprise rather than the property of individuals. It is also worth noting that many of Franklin's investigations, particularly those that remained most private and were less widely known, represented dead ends or experiments that did not lead to significant discoveries or practical applications. His investigations into electrical healing, for example, did not produce any therapeutic breakthroughs or contributions to medicine. His work on ocean currents and wind patterns, while contributing to general knowledge, did not lead to any revolutionary changes in ship design or navigation practice. His experiments with improved hearing aids and acoustic systems achieved limited success and had minimal practical impact in his own time. Yet it is precisely this willingness to pursue investigations, even when success was uncertain or unlikely, that distinguishes Franklin's approach to science. He did not demand that every investigation lead to practical results or revolutionary discoveries. He pursued investigations because they interested him, because the questions seemed worth asking, because the pursuit of understanding seemed valuable in its own right, even if the pursuit did not lead anywhere in particular. This attitude reflects a deep humanistic commitment to knowledge and understanding as goods in themselves, not merely as means to practical ends. In the final decades of his life, when Franklin was in his 70s and 80s, he continued to maintain his laboratory and to conduct investigations on topics that interested him, though necessarily at a slower pace than in his younger years. He would spend quiet hours examining specimens, making observations, recording notes, reflecting on the patterns he observed in nature. In his correspondence with other scientists and philosophers, he continued to discuss his investigations and to solicit the opinions and observations of others who shared his interests. He remained engaged with the scientific enterprise until the very end of his life, never losing his curiosity or his conviction that there remained much to be learned about the natural world. One of the most touching aspects of Franklin's legacy is the way in which his approach to science and investigation has continued to influence scientific thinking and practice down to the present day. The empirical methodology that he championed, the commitment to careful observation and measurement, the insistence on reproducibility and verification, the principle that scientific knowledge should be shared openly and subjected to community scrutiny, all of these principles remain central to how modern science operates. The idea that scientists should pursue investigations driven by curiosity and the desire to understand, rather than solely by the prospect of practical application or commercial gain, remains an ideal that scientists still espouse, even when practical and economic pressures often pull in different directions. Moreover, Franklin's model of the polymath, the person who pursues investigations across multiple disciplines and seeks to understand the interconnections between them, has experienced something of a revival in recent decades, as scientists have increasingly come to recognize that many of the most important and interesting problems in modern research lie at the intersection of traditional disciplinary boundaries. The problems of climate change, for example, require expertise in physics, chemistry, biology, ecology, oceanography, and atmospheric science, drawing on knowledge and methods from across the traditional scientific disciplines. The field of nanotechnology requires insights from physics, chemistry, materials science, and engineering. Franklin's conviction that nature was fundamentally unified and that important insights often came from connecting knowledge across disciplines has proven prescient. Let us consider for a moment what we might learn from Franklin's example as investigators and pursuers of knowledge in our own time. First and foremost, Franklin's life suggests that curiosity, genuine, sustained, passionate curiosity about the natural world, is valuable in itself, not merely as a means to professional success or commercial application. In our modern world, we often frame scientific research primarily in terms of its potential applications and practical benefits, and while these are indeed important, we should not lose sight of the value of investigation conducted simply because we desire to understand. Second, Franklin's example suggests that breadth of knowledge and the willingness to pursue investigations across multiple fields can lead to insights and connections that might not emerge from narrow specialization. While there are certainly significant advantages to specialization and deep expertise in a particular field, the greatest innovations often come from people who can draw on knowledge and insights from multiple disciplines and apply them in novel ways to new problems. Third, Franklin demonstrates the importance of patience and persistence in scientific investigation. Many of Franklin's most important discoveries and inventions were not the result of sudden inspiration or brilliant insight, but rather of years of patient, methodical investigation, repeated experiments, careful observation, and gradual refinement of ideas and designs. In our modern world, which often emphasizes innovation and breakthrough moments, it is easy to underestimate the value of the slow, careful, unglamorous work of systematic investigation that often precedes any dramatic discovery or invention. Fourth, Franklin's life illustrates the importance of maintaining detailed records and documentation of investigations, observations, and results. Franklin's legacy would be far less rich and detailed if he had not kept such meticulous notes and records of his work. These records allow us, more than 2 centuries after his death, to understand not just what he discovered, but how he discovered it, what his thinking process was, what dead ends he pursued, and how his ideas evolved over time. This detailed documentation also allows modern scientists to sometimes revisit Franklin's observations with modern tools and techniques, discovering new meanings and implications in observations that Franklin himself could not fully understand with the knowledge available in his time. Fifth, and perhaps most importantly, Franklin's example suggests the profound importance of maintaining intellectual humility, of recognizing that we do not know as much as we think we do, and that there is always more to learn about the natural world, no matter how much we already understand. Franklin conducted his investigations from his 60s onward with the same enthusiasm and sense of discovery that characterized his work in his younger years, never becoming complacent or convinced that he had said the final word on any topic. He remained open to new ideas, to evidence that might contradict his existing beliefs, and to the possibility that nature might reveal new mysteries that had not yet been imagined. As we reflect on the arc of Franklin's life and the trajectory of his scientific investigations, we are struck by a kind of quiet grandeur in his approach to knowledge and understanding. He was not pursuing fame or recognition, though these came to him nevertheless. He was not seeking to build a great fortune from his inventions, though some of his developments could certainly have been monetized more thoroughly than he chose to do. Rather, Franklin seemed to be driven by something more fundamental, a deep desire to understand the world, to see the patterns and principles that governed the behavior of natural phenomena, and to apply this understanding in ways that could improve the lives of ordinary people and advance the collective knowledge of humanity. This motivation, this desire to understand for its own sake, coupled with a commitment to using knowledge for the benefit of others, remains as valuable and necessary today as it was in Franklin's time. In an era when science is increasingly driven by commercial interests and the quest for profitable applications, Franklin's example reminds us of the importance of protecting and nurturing the pure pursuit of knowledge, the investigation that is conducted simply because we want to understand. At the same time, his example reminds us that science is ultimately a human endeavor, carried out by human beings with human concerns, and that the most meaningful science is often that which connects with human values and seeks to improve human life and human flourishing. In the quiet of the evening, as you drift towards sleep, imagine Benjamin Franklin once more in his laboratory, perhaps in his later years, moving slowly among his instruments and apparatus, examining a specimen or conducting a final measurement before the day ends. The candles flicker softly, casting dancing shadows on the walls, and in the gentle light, Franklin continues his work, not driven by ambition or the prospect of fame, but simply by the endless desire to understand, the perpetual curiosity that never quite fades away, no matter how old we become or how much we already know. This image of Franklin, the patient investigator, the humble seeker of knowledge, the person who believed that understanding the natural world was one of the greatest pursuits available to human beings. This is perhaps his greatest legacy, more valuable than any invention or discovery. The experiments have ended, the laboratories have been closed, the instruments are silent. But the spirit of investigation that Franklin embodied, the commitment to careful observation, systematic inquiry, and the pursuit of knowledge in all its forms, lives on in every scientist and investigator who has chosen to follow a similar path. As you close your eyes and drift into sleep, may you carry with you the quiet inspiration of Franklin's example, a reminder that the world is full of mysteries waiting to be understood, that patience and persistence often yield the greatest rewards, and that the pursuit of knowledge is one of the noblest of human endeavors, worthy of our time, our attention, and our deepest commitment. And so concludes our journey into the secret experiments of Benjamin Franklin, the lesser-known scientific pursuits of America's most versatile founding father. May his example inspire us to look more deeply into the world around us, to ask questions about how things work and why they behave the way they do, and to maintain throughout our lives that sense of wonder and curiosity that characterized the investigations of this remarkable man.